In this episode,
The leap in capabilities is just tremendous.
In a way, it feels like I'm stepping into the future.
the world's most advanced fighter aircraft.
Bottom line, it's an engineering marvel.
There's nothing in the world that comes close.
And the pioneering historic innovations
Wow, how this airplane flies. Look at that.
This is phenomenal. Absolutely phenomenal.
that made the impossible possible. The United States military, home to the largest fleet of fighter aircraft on the planet. They're the essential tool of modern warfare.
Carrier, strike group 10.
Capable of defending airspace over land and at sea, anywhere on the face of the Earth. But with the potential for conflict to arise at any moment, staying one step ahead of an unknown enemy with unknown capabilities presents an enormous challenge. Naval Air Station Lemoore in California is the master jet base of the Pacific Fleet.
Cobble 1-3, Lemoore ground taxi to line, Via Bravo.
Commodore Max McCoy is part of the team responsible for ensuring that the U.S. can maintain dominance of the skies.
Controlling airspace is absolutely critical. It gives us the flexibility to control the contested battle space. It gives freedom of navigation to respond anywhere in the world to an emerging crisis.
But ensuring that war in the air remains a one-sided fight is a relentless engineering battle, where technology can mean the difference between life and death.
7-3 is coming out now, Captain.
The United States needs to continue to develop new aircraft so that we can continue to dominate the battle space, both on the surface and in the air.
Today, engineers are pushing the boundaries of aviation technology further than ever before. They've created a brand new revolutionary fighter aircraft. The F-35 Lightning II. This multi-role fighter is the most technologically advanced aircraft in the world. Capable of handling threats in the air and on the ground. It will also be operated by 9 partner nation militaries, including the RAF in the UK, Italian Air Force, and Royal Danish Air Force.
For me, flying the F-35 is amazing. The aircraft's a combination of maneuverability, speed, altitude, endurance.
The aircraft is designed in 3 variants: the F-35A for the Air Force, B for the Marines, and C for the Navy. Each can reach a top speed of 1,200 miles per hour, over 400 miles per hour faster than the speed of sound. This immense power is produced by an engine capable of generating more than 40,000 pounds of thrust, making the F-35 a staggering 10 times more powerful than the first jet fighters, delivering nearly 22,000 pounds of weaponry anywhere on the planet.
The F-35 is the most capable, survivable, lethal, adaptable, and flexible airplane in the world today.
But this ambitious project presents some formidable engineering challenges. How do you design and build a single aircraft for 3 distinctly different branches of the military?
Building an aircraft that not only is a multi-role fighter, but has the reconnaissance capability, the advanced sensors that the F-35 has, is a challenge.
How do you make an aircraft traveling at almost 1,000 miles per hour disappear?
As a pilot, it's virtually impossible to comprehend the level of detail and advanced engineering required to make something roughly 50 feet by 40 feet virtually undetectable or invisible to radar.
And make an airplane weighing more than 20 tons defy the laws of physics.
When we set out with the engineering challenge of being able to take 40,000 pounds of airplane and land it vertically, almost seemed insurmountable.
Building the world's most advanced war machine is a challenge for Santi Bulnes, Vice President of Engineering for F-35 manufacturer Lockheed Martin.
Every service, whether it's Air Force, Navy, or Marine, really counts on its aircraft to go do what it needs to do. And it is important. Why? Because it is the first thing that you go into war with.
But after decades of each service using different aircraft, an ambitious plan is underway.
There have been several attempts in history to build a one-size-fits-all fighter for folks, and it's ended up being a little bit disappointing.
Santi and the team of engineers must learn from the mistakes of the past.
The military wanted a new aircraft to be able to do multiple things. It couldn't just be a one-trick pony. It needed to be able to fly far to go where it needed to. It needed to be able to go supersonic to achieve the speeds needed to be an effective fighter. It needed to be stealth so that it could penetrate enemy defenses.
To create the perfect plane, the team must look at how it was done by the pioneers that came before them. High above the Florida coastline,
What a fantastic airplane.
pilot Rob Collins is putting a game-changing piece of aviation engineering to the test.
I can't help myself. We're going to do that again. Look at that thing go around. Wow. Back in 1937, the U.S. Army Air Corps sent out a request for a new type of multi-role fighter.
This new aircraft would need to be capable of taking off from a short runway, climbing to 20,000 feet in 6 minutes, and having a top speed of 360 miles per hour.
This was a rather radical request at the time, and the engineers would really have to think outside of the box to develop a new design and engineering solutions that never before were possible.
Engineer Clarence Kelly Johnson and his team at the Lockheed Martin Corporation started development on a top-secret prototype. A project that would revolutionize the multi-role fighter aircraft.
This is the Lockheed P-38 Lightning, one of the most unique fighter planes of World War II, and I personally think the most beautiful. There's no fighter plane that has such a look. The twin booms, this gondola in the center, it is absolutely stunning.
Considered the first true modern multi-role fighter aircraft, the P-38 was capable of attacking targets in the air and on the ground, as well as carrying out vital photographic reconnaissance missions.
Back in the 1930s, and we have to remember, aircraft at that time were mostly open cockpit biplanes. To be the interceptor that the Army Air Corps wanted was a tall challenge.
To solve the speed challenge laid out by the Air Corps, engineers devised a simple solution.
Kelly Johnson came up with a very unique way of solving this issue. They made it twin engine, not a single engine fighter.
With no single engine capable of producing enough power to get the P-38 to 360 miles per hour, he added a second, doubling the amount of thrust.
The engines in the P-38 were an Allison 1710. They're a V12 liquid-cooled engine. In the L model, this aircraft here, they produce 1,600 horsepower each.
These two engines, combined with the aircraft's smooth aluminum flush-riveted design, pushed the P-38 to speeds nearly 100 miles per hour faster than other fighters of the day. and way over the Army Air Corps' requirements.
Making an engine that could fly high enough where it could be a successful interceptor at altitude, that was an amazing accomplishment back at that time.
But to be a success, the P-38 also had to meet the Air Corps' other requirement. To demonstrate this capability, Rob is once again taking to the skies.
Houston Radar ground, Lightning 505, Mike Hotel, American Aero, ready to taxi. 11.
Lucky 505, Mike Hotel, roger, taxi via Delta.
The Air Corps needed their new fighter to be capable of getting airborne using just over 2,000 feet of runway. So is the P-38 up to the challenge?
There's 45 inches. You can hear the turbos start to wheel. The whistling of the turbos are really pronounced in this airplane. There's about 1,000 feet, and we're off the ground. Wow, how this airplane climbs. Look at that. 2,000, 3,000 foot a minute rate of climb.
With a maximum climb rate of over 3,300 feet per minute, the Army Air Corps' final requirement had successfully been met. The P-38 was one of the most successful aircraft of the Second World War, achieving engineering feats beyond the reach of what was considered possible at the time.
It's an incredible aircraft to fly. It's so maneuverable, fast and responsive. And it really laid the foundation for modern fighter planes today.
Today, engineers are taking the lessons learned by their predecessors on the P-38 and inserting them into the DNA of the world's most cutting-edge weapon of war.
This aircraft is about as advanced as it gets in terms of technology.
The United States military has a new way of defending its airspace. Built to travel at 1.6 times the speed of sound, capable of withstanding 9 times the force of gravity, and it can strike anywhere on the planet.
This is the F-35C Lightning II. It's the U.S. Navy and U.S. Marine Corps' carrier-capable version of the Joint Strike Fighter designed to launch from and recover to Ford and Nimitz-class aircraft carriers.
Commander Mark Cochran is part of a small group of pilots trusted to fly the Navy's brand new over $100 million weapon.
The F-35 Lightning II takes its name from the P-38 Lightning, made by Lockheed Martin Corporation during World War II. Both aircraft were cutting edge for their day, both aircraft were multi-role, and both aircraft are going to be used across all theaters of conflict.
But despite their similarities, the F-35 is capable of things engineers in the 1930s could have only dreamed of.
All right, so from front to back, some sensors that you'll find on the F-35 are some mission systems. At the front, you're going to have an active electronically scanned array radar. They can locate targets just by their physical presence. After that, you're going to have the electro-optical targeting system. It's going to allow us to target aircraft and ground targets via their IR signature. Above that, you'll have the distributed aperture system, or DAS, which its primary function is missile warning, so to see missiles launched by another aircraft. However, it also provides the pilot the ability to see in the dark. Moving aft, we're going to have the largest wing of the F-35 family, and that's designed for increased maneuverability. It increases our range.
It's arguably the world's most cutting-edge weapon of war. But just like its predecessor, the F-35 still requires a human at the controls.
Sitting on the flight line or on the flight deck in an F-35, waiting to take off is one of anxious excitement.
Once airborne, Mark will be at the controls of a supercomputer capable of completing more than 400 billion operations a second, all while traveling at speeds up to 1,200 miles per hour.
5 Mike Hotel, give the tower call when you're ready.
The F-35's massive single engine puts out over 40,000 pounds of thrust, making it the most powerful fighter jet engine on the planet.
Airborne visibility is excellent, maneuverability is excellent, payload, range, altitude, airspeed are all better than our legacy fighters that we fly in the Navy. The F-35 is the smartest and most deadly aircraft in production.
Construction of the world's most advanced fighter jet begins at the F-35 factory in Texas. The task of turning raw materials into a fully fledged war machine is the responsibility of senior fellow Don Kennard.
There's about 7.5 million square feet total here in Fort Worth for building the airplanes plus storage.
Over a mile long and covering an area the size of over 130 football fields, the F-35 factory is one of the most advanced in the world.
Well, first of all, we get lots of parts. So for the wings and forward fuselages, we get composite parts, metal parts, tubes and wires from all of our suppliers.
Each station on the factory floor carries out a specific role. At one end of the mile, the forward fuselage, nose, and cockpit section is assembled. At the other, the wing sections are formed and mounted together. At final assembly, the control surfaces are added, and the F-35 gets its Pratt & Whitney engine before leaving the factory for final checks and flight testing.
This aircraft is about as advanced as it gets in terms of technology.
But making an aircraft this advanced requires more than just a well-oiled production line.
So in the old days, we used to take the drawings, and a mechanic would put out the drawing. These are 20, 30-page drawings, and he would start writing down on every fastener with a marker what fastener went in what hole, and then we'd get that panel on the airplane, and then they'd have to put it up, and then he'd follow that to put them in.
Today, through the use of optical projection, Don and his team are revolutionizing aircraft manufacturing.
What we're doing is I'm lighting up the fasteners on this big cover on the airplane. So for example, here, I'm saying I want to put this particular fastener in these particular holes. You get a lot better quality, making sure the right fastener goes in the right hole.
Thanks to systems like this, after more than 18 months of work, a completed F-35 rolls off the line, ready for deployment.
What comes in is a bunch of parts, pieces, and components from all over the world. What leaves here is a completed F-35.
But now engineers face one of the toughest challenges in the history of aviation.
The F-35 is a 40,000-pound class aircraft, so when you have to hover and land a 40,000-pound airplane, it is quite a challenge.
As they attempt to defy the laws of physics. In Fort Worth, Texas, a revolution in aviation engineering is occurring. Engineers are building the most technologically advanced fighter jet on the planet, the F-35 Lightning II. Made from over 250,000 individual parts, it takes over 18 months to turn the raw components into a state-of-the-art fighting machine. But before the F-35B variant can get in the air, engineers face another challenge.
The Marines wanted an aircraft that would land on their smaller carriers, not as large as what the Navy has, so those carriers require an aircraft that will land vertically as the Harriers do today.
First entering service with the Marine Corps almost half a century ago, the Harrier has been the aircraft of choice thanks to its almost unique ability, the vertical landing.
So the Marines wanted this plane to have maximum flexibility for them to be able to fight their wars.
But hovering an airplane that's over twice the weight of the Harrier challenges every rule of aeronautical engineering.
The F-35 is about a 40,000-pound aircraft, and getting that much weight to hover, and to hover in a stable fashion, is an engineering challenge.
To pull it off, the team will have to travel back in time. At a secret location in the USA, test pilot Andy Edgell is uncovering a unique aircraft that transformed aviation engineering on Earth and in space.
Very excited. This is one-of-a-kind aircraft. This is the Bell X-14. This is the only one in the world. This is the only X-14 that was ever built. What a fantastic machine.
Built under top-secret conditions in the 1950s, the X-14's mission was to see whether it was possible for a jet airplane to take off and land vertically.
The big challenge is here you've got a 4,000-pound aircraft on Earth. Gravity takes effect, tries to pull it down to the ground. If you want to just take the aircraft off vertically, all of the thrust that you need to achieve needs to go straight up, and it needs to be bigger than the weight of the aircraft.
Designed by engineers at the Bell Aircraft Corporation in New York, the X-14 prototype was constructed mainly from existing parts in just 3 months.
All right, let's pull this out and have a good look at her.
In order to understand the engineering behind this one-of-a-kind airplane, Andy has to move it out of the hangar for the first time in decades.
Pretty phenomenal moment to pull this one out. These two engines, they're tucked neatly into the fuselage. They're not out on one wingtip and the other wingtip. And the reason for that is you want everything all nice and close and in line with the center of the aircraft. Because eventually what we're going to try and do is balance this aircraft on a column of air.
Each engine produces over 3,000 pounds of thrust, enough power for a conventional takeoff. However, the key to vertical lift and landing isn't producing thrust. It's directing it precisely.
This is where the magic happens. This is the crown jewels of the X-14. The air that comes out of the engine, that exhaust, gets pushed out in a direction that is decided by the pilot. So the pilot can choose which way he rotates these nozzles and directs these vanes. In doing that, what he's essentially deciding is where to propel the air out of the back of the engine. If he positions the nozzles to go straight down, the aircraft will go up. And there, when it's coming straight down, the aircraft is just balancing on a column of air. What we see here is the first ever thrust vectoring aircraft.
The team at Bell had solved one of the greatest challenges in aviation engineering. But this was only half the battle. Now they would have to engineer a control system that would allow pilots to pull off the unthinkable. In the late 1950s, engineers at the Bell Aircraft Corporation tested their prototype for the first ever thrust vectoring aircraft. The X-14 successfully completed a vertical takeoff. Next, they had to pull off the landing.
Now, in conventional flight, when you're going forwards through the air and the air is blowing over the wing, we control it by moving these surfaces. They're called the ailerons. If the pilot wants to move left, he moves the stick to the left aileron goes up, the right aileron goes down, and that means more lift is produced on the right wing than the left, and the aircraft rolls left. Very simple. So the situation we're looking at right now is exactly the same as the situation when the X-14 is sat in the hover. The pilot can move the stick all he likes, and the ailerons will move all they like, but the aircraft's not rolling.
The system works by taking excess air from the engines and directing it to nozzles located on the wingtips and rear fuselage. As the pilot moves the stick, the nozzles either open or close, releasing high-pressure blasts of air, directing the aircraft in roll, pitch, or yaw.
So when I move the stick to the left, the duct closes. There's no jet of air that comes out. There's a big puff of air that comes out on the other side, and the aircraft rolls.
The X-14 rewrote the aeronautical engineering rulebook, becoming the first American jet aircraft to achieve the vertical takeoff, transition to conventional flight, and vertical landing.
Now this is incredibly exciting for me. I can officially say that I have sat in an X-plane. I can immediately identify that here is the nudging of the nozzles, and it even says horiz for horizontal and vert for vertical. So if I were to pull back on this switch here, it's going to rotate my nozzles down and sit me nice and stable on top of that column of air.
After proving the concept of vertical takeoff and landing was possible, in 1959, the X-14 was transferred to NASA, where it helped train Apollo astronauts to overcome the biggest engineering challenge in history, landing on the moon.
And the fact that Neil Armstrong was sat in this seat flying this aircraft, this is a once-in-a-lifetime opportunity that I just never thought that I would get. For its time, the X-14 was groundbreaking. There was nothing like it in the world. Everything after it evolved from this. They proved the concept in the X-14. They made it better in the Harrier. They improved it further in the F-35, but it all started here in the X-14.
For the F-35B, engineers have taken the raw elements of the X-14 and improved them for modern warfare. At the F-35 factory in Texas, Chief Test Pilot Alan Norman is getting hands-on with this upgraded thrust vectoring system.
One of the easiest things about the airplane is, honestly, one of the hardest things about other airplanes, which is to get this airplane in the configuration to hover and the ability of this airplane to hover. For the pilot, all it is for us is a few button switches.
The centerpiece of the F-35B's thrust vectoring capability is its Rolls-Royce lift fan. As the pilot engages hover mode, it reveals itself and begins rotating, reaching 29,000 horsepower. Connected to the main engine via a drive shaft, it produces a downward-flowing column of air at the front of the plane. At the rear, the exhaust nozzle twists, aiming its thrust toward the ground. For directional control, bypass thrust from the main engine is directed to outlets located under the wings, allowing the F-35B to gently touch down. But vertically landing an aircraft that weighs almost 20 tons on a carrier in the middle of the ocean is a challenge.
Well, we have a ship out in front of us. We're in the transition to a hover mode. The engine's twisted around, the lift fan is engaged, and then we're coming abeam the ship at sea. We'll pull next to it and then try to land aboard it. So we'll come down in altitude, and you can see off to my right is the ship. And now that I've picked out where I'd like to come down, I can come right down on the deck. Piece of cake.
The F-35B's lift fan system is genuinely unique in the world of aviation.
My first impressions when I saw the very first F-35 were, what is going on? To see 20 tons floating in the air, rock solid, not moving. I thought it was fantastic.
This technology will ensure the F-35B rules the skies for decades to come. But before it can get off the ground, engineers must overcome another complex obstacle.
To take an airplane that's basically 50 feet long and 35 feet wide and then make it nearly impossible for a radar system to see is a huge challenge.
The F-35 Lightning II. Capable of soaring over 50,000 feet above the Earth's surface. It can operate in desert heat or freezing cold and land vertically with near pinpoint accuracy. But for the F-35 to become the military's aerial weapon of choice, engineers must overcome a problem that's plagued previous generations of fighter aircraft.
This is the F-18 Super Hornet. I've flown both E and F Super Hornets for about 10 years and about 2,000 flight hours across 3 combat deployments.
In service since the mid-90s, the Super Hornet is now lacking an important feature essential to modern warfare.
Even though they're advanced, they still have a problem where they are visible to radar and they can't penetrate integrated air defense systems as far or as effectively as a newer, more modern aircraft.
As anti-air defenses have developed and improved, this visibility to radar can mean the difference between life and death.
If I were monitoring a radar console looking for an F-18 Super Hornet, without any other support, it'd be easy to pick it up.
But could the solution to making an airplane invisible to radar already exist? At the National Museum of the United States Air Force, retired pilot Mace Carpenter is uncovering the engineering secrets behind one of the most classified aircraft ever built.
Wow, this is incredible. I never thought I'd be an F-117 again.
Conceived in the midst of the Cold War, the F-117 was designed to slip undetected into enemy territory.
Radar has been a nemesis of strike aircraft since World War II. The bulk of enemy air defense systems use radar for acquisition and for target tracking, guiding their missiles into the aircraft. So the goal was to reduce the enemy's ability to be able to see the aircraft until it was too late.
At the top-secret Lockheed Martin Skunk Works in California, engineer Ben Rich and his team started plans for the world's first stealth strike aircraft. The problem they faced was finding a way to overcome decades of radar research and development.
This is kind of a rudimentary demonstration on how radar might work. The flashlight will be my radar transmitter, and the mirror is a conventional aircraft. If I shine my light directly on the conventional aircraft, the light comes back to me as a very bright beam, a very bright return. Now, if this beam that was returning to me was radar, I would be able to pick up the aircraft from a very long distance. This is what's happening with most aircraft in the world. They're easily tracked by radar, but when you're a strike aircraft trying to penetrate defended airspace, it's bad.
So instead of the smooth aerodynamic lines found on other aircraft, engineers started testing a faceted, angular-shaped airframe.
Now I have a different mirror, and again, the light is the radar. The mirror represents the F-117. When I shine a light on this mirror, the vast majority of the light is reflected away and not back at me. And this is how the F-117 works. The radar is largely reflected away.
By reflecting radar energy away from the aircraft, engineers were able to drastically shrink radar signature. But the F-117 would require further engineering to become a ghost of the sky.
The most important feature of the F-117 that makes it stealthy is the shape, 85% of the stealth. The other 15% is accomplished by putting radar-absorbing material, or RAM, onto it.
The exact makeup of this radar-absorbent material is still top secret, but it's believed to be made from thin sheets of a composite material, coated in iron ferrite paint that contains microscopic spheres. When hit by radar energy, these spheres vibrate, turning the energy to heat, which is absorbed by the plane, further reducing the reflection.
Hopefully, we were a ghost and not seen. If we were seen, we weren't seen for any more than we had to be, or not enough time for the people on the ground to react.
The introduction of stealth technology changed the way war is waged from the air.
When the F-117 was designed in the mid-70s, it was at the pinnacle of aviation design. There was nothing that could touch it for decades.
Now, engineers working on the F-35 have taken ideas behind the F-117 and enhanced them for modern warfare, with the help of the world's most advanced modern supercomputers. In the 1970s, with the introduction of stealth technology, the F-117 ushered in a new era that would enable the United States to dominate warfare for decades to come. Now, engineers are taking it one step further.
Where the F-117 was an early introduction to stealth technology, radar-absorbent material, the F-35 is the third step, or the third generation of that evolution.
Modern supercomputers have allowed engineers to calculate radar returns from curved surfaces, something not possible in the 1970s, giving the F-35 a vast aerodynamic advantage over its predecessor.
Lucky 505 Mike Hotel, roger, taxi via Delta.
But despite this gigantic leap in technology, one thing remains the same.
The low observable technology that's resident in the F-35 is highly classified. You have to have a validated need to know and be part of the program in order to access it.
What can be revealed is that just like the F-117, the shaping of the F-35 provides most of its stealth capability.
If you look at the aircraft top down, you'd see that the front edge, the forward edge of the wing is going to match the front edge of the horizontal tail, which is the aft control surface.
Known as planform alignment, This improved stealth design orients key flight surfaces at the same angle. As a result, radar energy is scattered away from the receiver in a precise direction rather than diffusing it where it could still potentially be detected.
Low zero technology isn't something that has an on-off switch. It's something that has to be built into an aircraft from the ground up.
The combination of all this engineering makes the F-35 a ghost of the sky.
What it provides to you is it gives you more space to operate in. So because I don't have to worry about a threat seeing me as far away, that's white space in which I can move in and operate on my own terms.
For the team behind this incredible airplane, the sense of achievement is clear.
The F-35 is the most incredible aircraft ever constructed. You look at how well it flies, when you look at how well it does its mission, this aircraft's going to be enduring for this country and its partners for decades, and I'm very proud of that.
By looking to great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
Every time I fly one of these airplanes here at the factory, I'm so proud. I see them flying in the air at a base, and I feel like a proud papa when I look up in the sky and see my kids up there flying. It's tremendous.
Engineers have built an age-defining airplane and succeeded in making the impossible possible.
I was a child of the Apollo era. You know, I stayed up late one night to watch them land on the moon. I was taken by that, and probably that influenced my whole life. Just being able to see something like that, you knew it was a miracle that we were there, a technological miracle, and the F-35 is that kind of program.